Hello, everyone. Today we're going to talk about annuities due. We discussed annuity immediate. That's when the payment happens in the end of each time period. But now we have annuity due, which the payment happens at the beginning of each period. So that's difference. Okay. The basic annuity due, which means the payment is $1 at the beginning of each of the interest period. We have a notation for the present value, which is 8. Let me draw the timeline first. Maybe that's better for the illustration. So you have time 0, 1, 2, ... n. Now you pay $1 at the beginning of each time period. And then here you have a $1. And then you have n payments, okay? You don't have anything here. Here you don't have it because in nth period, the $1 happens at the beginning of that period. So this time we got nothing. Okay, so that's the timeline of the annuity due. The present value, which happens here, is the notation is A, 2 dots, sub n angle I. Okay, and the future value it happens here. It's S, 2 dots, and angle, sub n angle I. Okay, so these are the notations. So what is the formula? So let's work with A 2 dots, the present value. Okay, so you have a $1, and then you have a V, and then you have V squared plus dot 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 plus V to the n minus 1. Okay. That equals, well, and V to the n minus 1 is for this one. Discount back at time 0. So that's 1 minus V to the n over V. That's 1 minus 1 plus I to the negative n over, I always forget, it's not 1, it's 1 minus V. Okay, it's 1 minus V. Eventually you have the bottom like D for annuity immediate of I, so that's why I forgot 1 minus L, 1 minus, so it's 1 minus V. 1 minus V, 1 over 1 plus I, so you have I over 1 plus I, which is exactly D, so we have that formula. So this is the annuity due, the present value of the annuity due, which is 1 minus 1 plus I to the negative n over D. Okay, it's a little bit squeezed. For the future value, we have 1 plus I to the n. So you have 1, 2. So you look at this $1. You have 1, 2. So accumulate to n. So you have 1 plus n. Then you have 1 plus I to the n minus 1, and so forth. In the end, you have a 1 plus I. Okay, that's this thing, $1 at the beginning of nth period, and the accumulated value at the end of the nth period is 1 plus I. So you have 1 plus I, move it out. You have a 1 plus I plus dot 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 plus 1 plus I to the n minus 1. That's 1 plus I times 1 plus I to the n minus 1 over 1 plus I minus 1. So I have 1 plus I to the n minus 1 over, you have I on the bottom here, but then I'm going to move this thing to the bottom. It's actually divided by. So you have I divided by 1 plus I. I divided by 1 plus I, that's D. So I have this formula for the future value, 1 plus I to the n minus 1 over D. Okay. So for annuity immediate, we have I on the bottom. For the annuity of annuity due, the bottom is D. Okay. And the formulas are given here. I wanted to say a little bit more about the amount, the relations amount annuity immediate and annuity due. Okay. I probably need a little bit more space, so I'm gonna draw here. Okay. So this is a time 0, 1, 2, dot, dot, dot. Let's say this is n minus 1, n. So totally you have n periods. Okay, that's no problem. It's n periods. For annuity immediate, I'm gonna use different color. Annuity immediate, you have $1 at the end of each time periods, and then $1 and $1. Totally you have n payments. Okay. And for annuity due, we have $1 here and $1 here, $1 here, and then you have a $1 here. That's it. Okay. And we have this notation for the present value. And we have this notation for the annuity present value of the annuity immediate. And here we have SN angle I, and also S2 dots and angle I. Okay. All right. So, obviously, well, actually, it's not that obvious. I need to talk about it. Here AV is the just future value. Okay, for some reason the textbook uses amount value, so I use FV future value. It doesn't really matter. So it's the future value. This is also future value. Okay. All right. So first of all, the relation between these two quantities is this. So A two dots sub n angle I equals 1 plus I times A sub n angle I. Okay, to see this, I probably needed to extend the timeline backwards one time period. Okay, so something like that. Okay. So it's like a time -1. It's just an artificial, imaginary thing to talk about. And for the red, so for these payments, okay, I have A sub n angle I here at -1, because you look at this cash flow, and at this time, you have the annuity immediate. Okay, so you have A sub n angle I here at time -1. For the red uh, cash flow. Okay, so now you see this value, happens one time period later than that. So if you accumulate this, you multiply this by 1 plus I, you would get the annuity due. Okay, so we have this relation. All right. And similarly, for the for the future value, it's very similar. So you can consider this at this time. Okay, let me use the orange one. Orange one. Okay. For the the red one. Red one. For this cash flow again, and at time n minus 1, I have S and angle I. Okay, still n because actually you have n payments. Okay, if you consider starting from -1, 0 to n minus 1, you still have n periods, and each $1 happens at the end of each period. So it's S n angle I at time n minus 1. So we also have this property S two dots n angle I equals 1 plus I times S sub n angle I. Okay. Another relation between the annuity due and annuity immediate is that you consider the annuity due, which is let's look at this one. Okay, use red ink. Look at this one. Okay, you can consider it as this piece, this cash flow at $1, so that equals 1 plus, and the present value of this cash flow, that is exactly A sub n minus 1 angle I. Okay, it's annuity immediate because $1 is contributed at the end of each time period. Okay, remember it's n minus 1. It's this one. Okay, this cash flow. The first one is gone. That's here. All right. So we have this property. So let me do this. A two dots and sub n angle I equals 1 plus A sub n minus 1 angle I. Okay. Be very careful about two dots with and without two dots. Okay. All right. And for the future value, the idea is very similar. You can consider look at the orange cash flow. So you look at this orange cash flow. You single out this $1. So this one equals $1 plus S two dots and minus 1 angle I. Okay. We have that. Oh, it's not written here, but you can consider it like that. And the reason is like you actually have n minus 1 contributions for this cash flow. And at time n, this is annuity due. And you have n minus 1 payments, so you have that. And this $1 is here, okay? Or there's another way of thinking, which is this one. Okay, so the future value is S actually, so it's S due and angle I that plus 1 that equals A sub n plus 1 angle I. So S, not A. Okay, so why is that? Um, you can consider you can consider uh, a future value due with n payments, which is this thing. Let's you have that. Okay. So I wanted to. So what should I say? So what I'm saying is that you don't have you got 0 here, right? That's the for let's use the red ink. Okay. You don't have anything here for okay. You don't have anything here for the red inked cash flow. So I would add 1 here. So artificially add 1. Okay. But then you don't have that one, so I'm going to subtract 1. So you add 1 and it's artificial add 1 when you're going to subtract this 1 later on. Okay. Now you look at this red inked cash flow. You actually have n plus 1 payments. And these $1 happens in the end of each time period, assuming you get a start from later one, because the first at $1 is the end of this time period. Okay, so in total you have n plus 1 time periods, n plus 1 payments. So you have a S sub n plus 1 angle I. But that one is not there. So it's minus 1, you would get the original of this. All right. So this is like subtracting 1. But another way to think about this is adding 1. So basically, just add 1 here, and you would get without that $1, you have a S and S 2 dots. Get the annuity, the future value of annuity due, and you add $1 here, and you treat these $1 as payments at the end of each time period, and then you will have a S of n plus 1 angle I. Okay, so this plus 1 equals that. Anyway, I hope you understand what I'm saying here. It's a little bit probably not a good explanation, but I hope it's okay. All right. So these are the relations among these quantities. Okay. Uh, this graph. Okay, I don't need that one. So let's move on to examples. During 1998, Omar had a dividend payment of $100 directly deposited to his savings account on the first day of each month. That's due, annuity due. Find the cumulative value, so the future value, of these payments at the end of the year if his savings account had a nominal discount rate, nominal discount rate of 4.8% payable monthly. So this quantity is this actually. So D sub 12, that's monthly effective discount rate. It's 0.048 divided by 12. But we need J. its effective interest rate monthly. That's D over 1 minus D. All right. So we're looking for the future value, right? $100 times S, because the due, I have two dots here. I have 12 payments. We have a J. Okay, we need to find that J. Okay, so that is $100. I normally calculate S12 and J and multiply by 1 plus J. That's usually I would do. I am familiar with this formula. So 1 plus 0. Uh, 0.04, 0.004 over 0.996, which is J. Okay, this is J here. Raise the power by 12 minus 1 over. Okay, we actually have D here, so I'm gonna just put 0.004. Okay, instead of doing this. No, sometimes I do this, but this one, the bottom is D. Or D is already given, so it's pretty easy to put T here, so I don't need to change to 1 plus J and then J on the bottom, then put 1 plus J in the end. So I'm not going to do this. Okay, I just use the D formula. Okay, so this would be 1 plus I to the n minus 1 over D. Okay. All right, and then I calculate it out. Nothing fancy. What is the value? 1231.7912, I believe. Okay. All right. So that's this answer. That's this problem. Let's move on to the next one. This is a little bit complicated. Dr. Hillary Street began making contributions to a new retirement account on her 30th birthday. 30th birthday. She made a contribution of $4,000 at the beginning of each year through her 64th birthday. Starting at age 65 and continuing through her 80th birthday, she made a level withdrawal on her birthday. Find amount of these withdrawals if they completely exhaust the balance in her account. And annual effective interest rate is 6% until she is 65, then 5% thereafter. The problem is a little bit complicated. For a complicated problem, I really encourage you or suggest you to draw a timeline. That will make the problem a bit easier. Okay. So this is the 30th birthday. Let's say it's 0. So 30th birthday. And 1 is the 31st birthday. And 2 is the 32nd. And then we have dot, dot, dot. Move on to 64th birthday. 64th birthday, that's 64. And then 65. Sorry, actually it's not 30, it's 34. Yeah. It's 34. That's 64 minus 30. And then have 35, you have a 65. And then we have a 80th birthday. So 80th birthday, which is 50 here. All right, so that's the time. Here, like the n ends. Here's the years, the birthdays. Okay. So starting on 30th birthday, at that particular time, she contributes $4,000. I'm now going to put a dollar sign to save space. And till 64th birthday, so that's here. And then starting at age 65 and continuing, she would make a level withdrawal P. I don't know what that value is. We're looking for that value P till she is 80th birthday. 80th, what is the 80th? Yeah, 80th birthday. Okay. And interest rate for this period, up to 35, that's 60%, 0.06. And starting from here, the interest rate is 0.05. Okay. All right. We needed to set a point at the time where we wanted to work with. Then we can find the future value and the present value at that particular time. You can, I think it should be this one, okay, because that's where the interest rate changes. So I'm going to put the time at her 65th birthday. So this is the time I'm going to work with. Okay. All right. So I'm going to calculate the future value of the first part of the annuity. Because $4,000 happened, it was contributed at the beginning of each year. So we have annuity due. And at this time, okay, for the first annuity, it's future value. So I have a $4,000 and S two dots because it's annuity due. And actually there are 35, okay? This is the first payment, second payment, and 35th payment. N is actually 35. There are 35 payments, okay? 35 angle 0.06. This is the future value of the first part of annuity. And this amount will be supporting her withdrawal. So this is also equal to the present value of the next part of the annuity, which is has P. So you have P, and each P happens at the beginning of each year, so it's still annuity due, but it's a present value. And from 35 to 50, actually there are 16 payments. Okay, there are 16 payments. Okay. So what should we do? There are 16 payments, and we're looking at oh, I don't care actually. I don't care this time period. I don't care 80, 81. So it's just we're looking for the present value of this annuity at this point. So I only need to care about the number of payments, 16 and 0.05. Okay. And now we can solve for P. It's a little bit complicated, so let's plug in the formula. So 4,000 times 1 plus 0.06 to the 35 minus 1 over 0.06. That is actually S without two dots, but then I'm going to multiply by 1.06. That will give us the S two dots. So that equals P times, it's A, so it's a present value. So 1 minus 1.05. So I'm already added 0.05 to 1, okay? And to the negative 16. And then divided by 0.05, and then you multiply by 1.05. Okay, so you get annuity due. Okay, so we calculate the left side is 472483.4666. That's I'll keep 4 decimal points to be a little bit more accurate. The right side, this quantity is 11 point. Get rid of that line. It's annoying. So I just show you this number is 11.379658. And then you divide this number by this number, you would get P. P is what? P is 41520.01. All right. So that's this problem. And this is actually a very common problem. I would really want you to know it's in reality, it happens quite often times. You contribute money, putting them into an account, you accumulate, right? When you are working. And then when you retire, you get money from that account. So the key thing you need to be aware of is that when the time Hillary was retired, the value for the first annuity is actually future value at that time, and that future value is the present value for the next part of the annuity. So that needs to be very careful here. So for the first type of for first part of the annuity is S, and for the second part is A. All right. That's okay. Get rid of everything. Do I have another problem? Okay, so yes, there's another problem. Investment contributions of $4,500 are made at the beginning of the year due for 20 years into an account. This account pays an annual effective interest rate 7%. So I is no, I is 0.07. 20 years, n equals 20. Okay. Calculate accumulated value at the end of 25th year, and at the end of here's at the beginning. So you need to be very careful. Okay. I wanted to draw a timeline. It's very helpful to draw a timeline to make everything clear. All right, time 0 here, 1, 2, and then 19, 20, 21, and then you have a 25. That's the end of 25. A contribution of $4,500, okay, are made at the beginning of the year for 20 years. So actually the last payment happens at the beginning of the 20th year, which is also the end of the 19th year. So it's here. And we're looking for the future value at this time, okay? So you can do, you can set the time to be 20 and work for the future value of this annuity, and then accumulate it to the time 25. So you can do this. You can do 4500. You have S 2 dots. It's the annuity due because all these $4,500 happen at the beginning of the year. And you have 20 payments, and you have 0.07. Okay, so this time. And then you multiply by 1 plus I, which is 0.07, to 1, 2, and 5 years. Okay, so this is the amount we're looking for. Or you can consider you're sitting at this time. Okay, and then you actually have a 4500 times S without two dots, because now you are treating all these contributions at the end of each year. But then you still have a 20 payments. That's no problem. The number of payments doesn't change. It's just like you're treating them as the end of each year. You can do that. That's fine. Now, this amount, okay, this amount will accumulate to the end of 25th year. So you have to accumulate 1, 2. So you need to multiply by 1 plus 0.07 to the 6, because that's 6 years, starting from the end of 19 year to the end of 25 years. So obviously these two are the same, okay? Because this is basically this quantity times 1.07. So you have 5 here, you have 6 here. All right, anyway, you would get a number 276,854.30827. I don't know, so it's 31 cents. Okay. So I think that's the answer. All right. Okay, so that's for this problem, and I think that's about annuity due. The next class, we're going to talk about perpetuity. These things, annuity immediate and annuity due sometimes are mixed together in a problem, sometimes a very complicated problem involving all these things. Probably we'll have some examples there. But for the introduction of annuity due, that's it. I'll see you the next time. Bye bye.